Welcome to a journey into one of the most captivating mysteries of modern science. Picture yourself witnessing an invisible cosmic dance, entire galaxies spinning far faster than they should, clusters of stars held together by an unseen force, and a universe that seems to be hiding 85% of its mass in plain sight. This is the fascinating realm of dark matter, the greatest enigma of the cosmos. Today, we're venturing into a territory that has puzzled the brightest minds in physics for decades. Scientists first stumbled upon this mystery when they noticed something peculiar. The outer regions of galaxies were moving much too quickly. According to our understanding of gravity and the visible matter we could detect, these stellar systems should have been torn apart. Yet there they were, spinning in perfect harmony, held together by something we couldn't see. This revelation opened a Pandora's box of questions that continue to challenge our understanding of the universe. As we delve deeper into this cosmic mystery, we'll uncover the remarkable chain of evidence that led to this groundbreaking discovery. From the gravitational lensing that bends light around massive cosmic structures to the intricate patterns in the cosmic microwave background radiation, each piece of evidence adds another layer to this compelling puzzle. The implications of dark matter's existence stretch far beyond mere scientific curiosity. This invisible substance appears to be the cosmic architect, shaping the very structure of our universe. It forms the scaffolding upon which galaxies are built, influences the birth and death of stars, and played a crucial role in the evolution of the cosmos since its earliest moments. What makes this journey particularly exciting is that we're not just studying ancient history, we're living through one of science's greatest detective stories. Right now, in laboratories deep underground and in sophisticated observatories worldwide, scientists are working tirelessly to detect and understand this elusive substance. Their quest combines cutting-edge technology with profound theoretical insights, pushing the boundaries of human knowledge. Before we embark on this fascinating exploration, I invite you to join our growing community of cosmic explorers. By subscribing to Exploring the Universe and activating notifications, you'll ensure you don't miss any of our weekly journeys into the cosmos. Each episode brings you face-to-face with another celestial mystery, carefully crafted to spark your curiosity and expand your understanding of our magnificent universe. In the grand theater of scientific discovery, few stories are as compelling as the revelation of dark matter. Let's travel back to 1933, when Swiss astronomer Fritz Zwicky made an observation that would shake the foundations of our understanding of the universe. While studying the Coma cluster, a massive collection of galaxies approximately 321 million light-years from Earth, Zwicky noticed something profoundly strange. The galaxies within the cluster were moving at speeds so incredible that they should have broken free from their gravitational bonds and scattered across space. Picture a carnival's Ferris wheel spinning at such an impossible speed that it should fly apart into pieces, yet somehow defying all logic it remains perfectly intact. This was exactly what Zwicky was witnessing on a cosmic scale. Using the virial theorem, a fundamental principle of physics that relates the average kinetic energy of a system to its total potential energy, Zwicky calculated that the cluster needed about 400 times more mass than what was visible to hold itself together. This missing mass, which he termed dunkle Materie, or dark matter, seemed to provide the invisible gravitational glue keeping the cluster intact. However, like many groundbreaking discoveries, Zwicky's observation remained largely overlooked for decades. It wasn't until the 1970s when astronomer Vera Rubin, along with her colleague Kent Ford, provided the most convincing evidence for dark matter's existence. Their work focused on something seemingly simple yet profound: how stars move within galaxies. Rubin meticulously studied the rotation curves of galaxies, graphs showing how fast stars and gas orbit around their galactic centers. According to our understanding of gravity, stars at the outer edges of galaxies should move much slower than those closer to the center, just as planets farther from the Sun orbit more slowly. However, Rubin discovered something remarkable. The outer stars were moving just as fast as the inner ones, creating what we now call flat rotation curves. This observation was revolutionary. The only way to explain these flat rotation curves was if galaxies were embedded within massive halos of invisible matter. These dark matter halos would need to extend far beyond the visible edges of galaxies, providing the extra gravitational force necessary to maintain these unexpectedly high orbital speeds. To better understand this, imagine a ballerina performing a pirouette. Normally, when she extends her arms, she slows down due to the conservation of angular momentum. But in Rubin's observations, it was as if the ballerina maintained the same rapid spin regardless of her arm position, a complete violation of what we expected from the visible mass alone. The implications of Rubin's work were staggering. Not only did it confirm Zwicky's earlier observations, but it also suggested that dark matter was ubiquitous, present in virtually every galaxy we could observe. Her meticulous measurements indicated that visible matter, all the stars, planets, dust and gas we can see, makes up only about 15% of the total mass in galaxies. The remaining 85% exists as this mysterious, invisible dark matter. This discovery marked a paradigm shift in our understanding of the cosmos. It wasn't just a minor adjustment to our models. It was a fundamental revelation that most of the universe's mass exists in a form completely different from the ordinary matter we're familiar with. The work of Zwicky and Rubin opened the door to a new era in astronomy and physics, launching countless research programs and theoretical investigations that continue to this day. The search for dark matter has since evolved into one of science's most sophisticated endeavors, employing everything from massive underground detectors to space-based telescopes. Each new observation and experiment adds another piece to this cosmic puzzle, bringing us closer to understanding the true nature of this elusive substance that shapes our universe. Let's dive into the compelling evidence that has convinced scientists of dark matter's existence. While we cannot directly see this mysterious substance, we can observe its gravitational effects on the visible universe, much like detecting an invisible person walking on a beach by following their footprints in the sand. One of the most spectacular pieces of evidence comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Imagine holding a magnifying glass above a text. The glass bends light rays, distorting and magnifying the words beneath it. In space, massive objects act similarly, bending and focusing light from distant galaxies. When we observe this bending of light in space, we often find it's far more pronounced than what visible matter alone could cause. This excess bending reveals the presence of dark matter, acting like an invisible cosmic lens. To better understand this, picture a rain shower falling on an invisible sculpture. While you can't see the sculpture itself, you can observe how the raindrops' paths bend and curve around its shape. Similarly, when we observe distant galaxies, we can see their light bending around massive cosmic structures in patterns that can only be explained by the presence of significant amounts of unseen matter. Perhaps the most striking evidence for dark matter comes from what we call the bullet cluster, what some scientists consider the closest thing we have to a photograph of dark matter. This remarkable cosmic collision between two galaxy clusters, observed in 2006, provides what many consider the smoking gun evidence for dark matter's existence. When these clusters collided, something fascinating happened. The ordinary matter, primarily in the form of hot gas, slowed down and stayed in the middle of the collision, like two clouds of smoke merging. However, the gravitational effects continued moving through unimpeded, as revealed by gravitational lensing. This separation between where we detect the normal matter through X-ray observations and where we detect the gravitational effects through lensing provides compelling evidence that most of the cluster's mass exists in a form that can pass right through ordinary matter without interacting, exactly what we expect from dark matter. Think of it like two schools of fish swimming through each other. If the fish represent dark matter, they would pass right through each other without colliding, while the water they disturb, representing ordinary matter, would create turbulence and remain churning in the middle. This is precisely what we observe in the bullet cluster. The visible matter stays behind while the invisible mass continues moving, creating a natural separation between ordinary and dark matter. Additional evidence comes from the cosmic microwave background radiation, the afterglow of the Big Bang. The pattern of temperature variations we observe in this ancient light can only be explained if dark matter was present in the early universe, helping to shape the cosmic structures we see today. These temperature fluctuations act like a fossil record, preserving the distribution of matter in the infant universe. We also find evidence in the way galaxies cluster together across space. Dark matter appears to form a vast cosmic web, with ordinary matter collecting along its filaments. This web-like structure, revealed through extensive galaxy surveys, matches perfectly with computer simulations that include dark matter, but fails to appear in models without it. The combined weight of all this evidence, from gravitational lensing and galactic rotation curves to the bullet cluster and cosmic web structure, presents an overwhelming case for dark matter's existence. While we still don't know exactly what dark matter is, we can map its distribution and measure its effects with remarkable precision. What do you think dark matter really is? Could it be tiny particles we haven't detected yet? Or perhaps something even more exotic? Share your theories in the comments below, and if you're as fascinated by these cosmic mysteries as we are, don't forget to like this video and subscribe to The Exploring Universe. The leading candidate in our search for dark matter's true identity is a class of particles called WIMPs, weakly interacting massive particles. Think of WIMPs as cosmic ghosts. They have significant mass, but barely interact with ordinary matter. Imagine throwing thousands of ping-pong balls through a chain-link fence. While most would pass straight through the gaps, occasionally one might hit the metal and bounce back. This is similar to how WIMPs are thought to interact with normal matter. Rarely, but just enough that we might be able to detect them. Deep underground, in some of the most sensitive detectors ever built, scientists are hunting for these elusive particles. These detectors use ultra-pure materials and sophisticated equipment to try to catch the extremely rare occasions when a WIMP might bump into an ordinary atom. The experiments must be conducted far underground to shield them from cosmic rays and other interference that might mask the subtle signals they're looking for. Another intriguing candidate is the axion, a hypothetical particle first proposed to solve a different puzzle in particle physics. Axions, if they exist, would be incredibly light, much lighter than WIMPs, but could exist in such enormous numbers that they could account for all the dark matter we observe. To understand axions, imagine a vast ocean of tiny, nearly massless particles, each contributing just a tiny bit to the total mass, but collectively creating powerful gravitational effects. What makes axions particularly elegant as a solution is that they weren't initially proposed to explain dark matter at all. They emerged from theoretical work, trying to understand why certain nuclear forces behave the way they do. The fact that they could also explain dark matter makes them an especially attractive candidate, like finding that a key made for one lock unexpectedly opens another. However, there's another, more radical possibility. What if our understanding of gravity itself needs revision? This is the premise behind modified Newtonian dynamics, or MOND. Rather than proposing new particles, MOND suggests that gravity behaves differently at very large scales than it does in our solar system. It's like discovering that the rules of a game change when you play it in a much larger arena. Mond can explain some observations remarkably well, particularly the flat rotation curves of galaxies that first suggested the presence of dark matter. However, it struggles to explain other phenomena like the behavior of the bullet cluster or the patterns we see in the cosmic microwave background radiation. Still, it reminds us to keep our minds open to radical possibilities. Some scientists are exploring even more exotic explanations. Could dark matter be composed of primordial black holes formed in the earliest moments of the universe? Might it be a manifestation of extra dimensions we can't directly observe? Could it be related to the mysterious dark energy that appears to be accelerating the universe's expansion? The search for dark matter has led to unprecedented collaboration between particle physicists, astronomers, and cosmologists. Advanced experiments are underway worldwide, from the Large Hadron Collider at CERN, which might create dark matter particles in high-energy collisions, to sophisticated space telescopes mapping the distribution of dark matter across the cosmos. Each theory has its strengths and challenges. WIMPs provide a natural explanation for the amount of dark matter we observe, but have stubbornly avoided detection despite decades of searching. Axions offer an elegant theoretical solution, but require extremely sensitive detection methods that are still being developed. Mond reminds us that sometimes the most revolutionary discoveries come from questioning our fundamental assumptions. As we await definitive evidence, the possibility remains that dark matter might be something even more exotic than any of our current theories suggest. The history of science teaches us that nature often surprises us with solutions more creative than our imaginations can conceive. The hunt for dark matter represents one of humanity's most sophisticated scientific endeavors, combining cutting-edge technology with innovative research methods across multiple frontiers. Let's explore the three main approaches scientists are using to crack this cosmic mystery. Deep underground, a new generation of detectors represents our first line of investigation. These extraordinary instruments are housed in some of the world's most isolated locations, often in abandoned mines more than a mile beneath the Earth's surface. This extreme depth isn't arbitrary. It serves as a crucial shield against cosmic rays and other background radiation that could interfere with dark matter detection. One of the most impressive of these facilities is the Xenon experiment, located beneath Italy's Gran Sasso mountain. Imagine a massive tank filled with ultra-pure liquid xenon, so clean that a single dust particle could compromise the results. This detector works like an incredibly sensitive cosmic security camera, waiting to catch the extremely rare moment when a dark matter particle might collide with a xenon atom. When such a collision occurs, it creates a tiny flash of light and a small cloud of electrons, signals so faint that they require the most sensitive photon detectors ever created to observe them. Similar detectors, like LX Zeppelin in South Dakota and PandaX in China, employ different technologies but share the same basic principle: creating the quietest, most sensitive environments possible to detect these ghostly particles. It's like trying to hear a whisper in a concert hall. You first need absolute silence. Meanwhile, at the Large Hadron Collider near Geneva, Switzerland, scientists are taking a different approach. Instead of waiting for dark matter to reveal itself, they're trying to create it. The LHC accelerates particles to nearly the speed of light and smashes them together with unprecedented energy levels. These collisions recreate conditions similar to those moments after the Big Bang, potentially producing dark matter particles. The challenge at the LHC isn't creating dark matter, it's knowing when you've created it, since dark matter particles would pass through the detectors without leaving a direct trace. Scientists look for their signature in missing energy and momentum from collision events. Imagine throwing two water balloons at each other and seeing the water spray in all directions, except one. That missing pattern might indicate something invisible carrying away some of the energy. The third frontier in dark matter research involves specialized telescopes and space-based observatories. These instruments don't look for dark matter directly, but rather map its gravitational influence across the cosmos. The Fermi Gamma Ray Space Telescope, for instance, searches for gamma rays that might be produced when dark matter particles collide and annihilate each other in space. Perhaps the most ambitious project in this category is the Euclid Space Telescope, launched to create the most detailed three-dimensional map of the universe's dark matter distribution. By studying how light from distant galaxies is distorted by gravitational lensing, Euclid can reveal the invisible scaffolding of dark matter that shapes our cosmos. Ground-based telescopes are also joining the hunt. The Vera C. Rubin Observatory, under construction in Chile, will conduct the most comprehensive survey of the night sky ever attempted. Its legacy survey of space and time will track billions of galaxies, helping us understand how dark matter has influenced the evolution of cosmic structures over time. These diverse approaches reflect the complexity of the dark matter puzzle. Each method has its strengths and limitations, and the breakthrough might come from any direction, or require combining insights from multiple approaches. Scientists are also developing new detection methods, including quantum sensors that could be sensitive to axion particles and novel ways to look for more exotic forms of dark matter. The search for dark matter has pushed technology to its limits, requiring innovations in everything from particle detection to data analysis. The sheer volume of data generated by these experiments has led to advances in computing and artificial intelligence, as scientists develop new ways to sift through the cosmic haystack for that elusive needle of dark matter evidence. The most astonishing revelation about dark matter lies in its fundamental connection to our very existence. Without this invisible cosmic scaffolding, the universe as we know it simply wouldn't exist. In the early universe, ordinary matter alone wasn't enough to create the gravitational wells needed for galaxy formation. The gravity of dark matter acted as a cosmic architect, creating vast structures that would eventually become the galaxies, clusters, and superclusters we observe today. During the universe's infancy, dark matter's gravitational influence began drawing ordinary matter together, creating dense regions where stars could eventually form. Think of it as an invisible hand, gently but persistently pulling cosmic material into concentrated areas. Without this process, matter would have remained too diffuse, too scattered to coalesce into the structures necessary for life. The implications are profound. The very stars that forge the heavy elements in our bodies, the galaxy that hosts our solar system, and the intricate cosmic web that makes up our universe's large-scale structure, all of these owe their existence to dark matter's hidden influence. When we look at our cosmic address, Earth, solar system, Milky Way galaxy, local group, Virgo supercluster, each larger structure in this cosmic hierarchy was shaped by dark matter's gravitational embrace. Even more remarkably, dark matter continues to act as a cosmic shepherd, its gravitational effects helping to maintain the stability of galaxies and preventing them from flying apart. Our own Milky Way galaxy, spiral arms gleaming with billions of stars, owes its very shape and stability to the massive dark matter halo that surrounds it. This realization transforms dark matter from a mysterious cosmic oddity into something far more profound, a fundamental cornerstone of our existence. We are not merely observers of dark matter's effects, we are its children, born in a universe whose very architecture was designed by this invisible force. The atoms in our bodies may have been forged in stars, but those stars could only exist because dark matter first created the conditions for their birth. In a poetic twist, we find ourselves searching for something that, in a very real sense, searched for us first, creating the cosmic conditions that would eventually lead to our emergence. This hidden matter, which we cannot see or touch, turns out to be one of the key authors of our cosmic story, an invisible hand that helped write the tale of our existence into the fabric of space and time itself. The quest to understand dark matter represents far more than just a scientific pursuit. It's a testament to human ingenuity and our relentless drive to push the boundaries of knowledge. This cosmic detective story has sparked technological revolutions that extend far beyond astronomy. The ultra-sensitive detectors we've developed in our search for dark matter particles have found unexpected applications in medical imaging, creating more precise diagnostic tools that can detect diseases earlier than ever before. The same technology we use to filter out cosmic noise in dark matter detectors is now helping to create more sensitive security scanning systems and improving our ability to detect environmental pollutants. But perhaps even more profound is what this quest teaches us about the limits of human knowledge and our capacity to transcend them. For centuries, we believed we understood gravity and matter completely. Then dark matter came along and shattered our assumptions, reminding us that the universe is far more mysterious than we imagined. This humbling revelation has actually empowered us, showing that our greatest discoveries often lie in the spaces between what we know and what we don't know. The search for dark matter has forced us to question our most basic assumptions about reality. We've learned that our ordinary human senses and intuitions, evolved for survival on a small planet, are inadequate for understanding the cosmos at its most fundamental level. Yet through mathematics, technology, and collaborative effort, we've found ways to extend our perception far beyond our natural limitations. This journey has taught us that the boundaries of human knowledge are not fixed. They are frontiers waiting to be pushed. There's an extraordinary beauty in living in a universe that still holds such profound mysteries. Every time we solve one cosmic puzzle, we uncover new questions that are even more fascinating. Dark matter reminds us that we live in a universe far richer and more complex than we ever imagined. It's a humbling reminder that even with all our technological advancement, we're still students of the cosmos, with so much left to learn. This ongoing mystery has united scientists across the globe in a common pursuit, transcending political and cultural boundaries. It shows us how the greatest puzzles of existence can bring humanity together, fostering collaboration and shared purpose in our quest for understanding. The search for dark matter has become a symbol of human curiosity and determination, reminding us that our species' greatest achievements often come from pursuing questions that seem, at first, impossible to answer. In the end, dark matter teaches us something profound about the human spirit, that we are capable of imagining and searching for things far beyond our immediate perception, that our quest for knowledge knows no bounds, and that the greatest discoveries often come not from what we can see, but from what we can imagine and deduce through careful observation and brilliant reasoning. This is the true beauty of living in a mysterious universe. It calls us to be our most creative, collaborative, and courageous selves in our endless pursuit of understanding. As we reach the end of our cosmic journey through the dark matter mystery, we find ourselves standing at a unique vantage point in human understanding. Perhaps the most captivating aspect of dark matter isn't just its elusive nature or its fundamental role in shaping our universe. It's how this cosmic riddle perfectly encapsulates the very essence of scientific discovery and human curiosity. Dark matter stands as a humbling reminder that our universe still holds profound mysteries, even in what we thought were well-understood aspects of reality. It teaches us that sometimes the most significant discoveries come not from finding what we expect, but from noticing what's missing, what doesn't quite add up in our calculations, and what challenges our most basic assumptions about the cosmos. This invisible cosmic companion has become a symbol of how science truly progresses, not in a straight line, but through a series of enlightening puzzles, where each solved mystery unveils new, even more intriguing questions. Just as we've learned that dark matter shapes the physical structure of our universe, the quest to understand it has shaped our scientific journey, pushing us to develop new technologies, imagine new possibilities, and expand our conception of what's possible. The story of dark matter reminds us that we live in an age of both tremendous knowledge and profound mystery. While we can map its distribution across the cosmos and measure its effects with incredible precision, its fundamental nature continues to elude us. This paradox of knowing so much yet so little captures the true spirit of scientific exploration. It shows us that the frontier of knowledge isn't a boundary to be feared, but an invitation to explore, to question, and to wonder. As we look to the future, we can be certain that our understanding of dark matter will continue to evolve, bringing new surprises and challenges. Yet it's precisely this uncertainty that makes the journey so compelling. Every new telescope, every underground detector, and every particle collision carries the potential for breakthrough discoveries that could revolutionize our understanding not just of dark matter, but of the fundamental nature of our universe. In the end, dark matter teaches us that the greatest scientific adventures lie not in what we know, but in what we have yet to discover. It stands as a testament to the endless frontier of human inquiry, reminding us that no matter how far our knowledge advances, the universe will always harbor mysteries waiting to be unraveled by future generations of explorers and dreamers.